All right, we're back. We are Game 2005 in the fall 2018 semester at George Brown. That's game physics. We're week 14, part 1 of our broadcast. We're talking about collision response. And this is the lecture part of the series. There's going to be more of the tutorial part coming up tomorrow, where I'll record whatever we did today. Okay, so let's bring up our PowerPoint. I've put this up on Blackboard already, so it's big. It's 113 slides, 18 slides. There it goes, pretty big. But it's not because I'm going to go through 118 slides. There's just no way. I'm not going to spend 2 hours going through every single slide. However, there are going to be some slides I spend more time on. So here we go. So part of this is going to be really loud, and other parts, let me just do that again. Yeah, that was really, really loud. Let's just turn that right off. Yeah. So part of this is going to be a lecture portion of this thing, and the other part is going to be the the portion which is to do with your programming. So that's the second half. So there's 2 halves to this thing. It's almost like 2 PowerPoints in one. Hell, you know what? It is 2 PowerPoints in one. All right. So here's the first part. So collision response, part 1, which is all around momentum and impulse, right? So remember we talked about it last week. I said that part of physics and the part we need to use with response, there's 2 types of responses, right? When we do a collision detection, we say, okay, 2 objects have collided, they've overlapped, something has happened, or whatever. Now we have to respond to it. And some of the simplest way to respond to things in our 2D and 3D games is an explosion, right? Something explodes, right? And that's not really a response for physics. That is like a cop-out. It's an explosion, it explodes, it's gone, and you don't have to worry about the physics response to it at all. It just disappears, right? Or it resets, like we talked about in class. This is not the collision response we're looking for. It's not the kind of thing we're talking about here. It's for physics, we need to talk about some kind of reasonable response, almost like more of a realistic motion, generated by 2 things colliding. So we're going to be talking about something called the conservation of linear momentum. And we have to talk about what momentum is. So we got to think about momentum being energy. Okay, so I've got this energy that's being generated by motion, right? So I'm moving already, and I've got energy that I've got stored up. In my mind, this is what I think about when I think about momentum. And then when I hit something, the momentum is transferred. The energy is transferred, but not lost somehow, right? Now that energy can be reflected, right? Or it can be absorbed, but that energy is not lost, right? So yes, this is like the mathy stuff that we talked about before. So the total momentum is equal to kind of the initial momentum plus the final momentum. It's the same momentum. It's like it doesn't go away, right? Which is what it looks like. And when we look at the components of momentum, we call them momenta. Yeah, it's a thing, right? Where we have like the initial momentum on the x-axis for one part, and the initial momentum on the x-axis for another part, and that equals to the final of part 1 and part 2 on the x-axis, the y-axis, or the z-axis is the same thing. But the idea here is when we look at the analysis model, momentum is not destroyed, it's conserved. Okay. Let's keep going here so we can get to this idea of momentum. So I'm trying to think of ways. So it's part of it. It must be internal to the system. So we talked about systems of energy, right? Remember we talked about systems being almost like a container. You can have energy that's being applied to a system, and the whole system is affected by the energy from outside. There's external energies and internal energies. Internal energy would be things like kinetic energy or potential energy. And some other external energy could be affecting the system and that kind of stuff. So this is all internal energies to the system itself, okay? So here's an example. We've got this archer. He's got a 60 kilogram weight or mass, and he's standing on a frictionless surface, ice, and fires this like arrow horizontally at 85 meters per second. With what velocity does the archer move across the ice after following the arrow, right? So when we talk about this, it's almost like I've got this momentum, but it's energy, almost like recoil that I'm firing. So I'm firing this arrow and I've got energy happening and the recoil is pushing the archer back. So how can we figure this out? Do we have enough information? So can we use like, the laws of motion? No, we have no information about velocities really in terms of like how much other than the velocity that is firing the arrow or speed, right? Can we use Newton's second law, force equals to ma? No, because we don't have enough information. How about the energy approach, kinetic energy and potential energy? No, but we can use momentum in this case, right? So we have to understand what momentum is. So again, I've got the information here in terms of, think about Newton's third law. For every reaction, there's an equal and opposite reaction, right? For every action, there's an equal and opposite reaction. So I'm firing a bow, I got recoil happening, and it pushes me back. I fire a gun, and there's recoil, and it pushes me back. And if I was on ice and I was firing a gun, I'd probably fall over, right? That kind of stuff. So there's almost this idea of conservation of momentum, and part of the momentum is absorbed in the firing, right? The other part is absorbed in the receiving, the collision, that kind of stuff, right? And we got some funky math happening here. Momentum is actually, we use a P to signify momentum. So the change in momentum will be 0 because we know that we cannot affect momentum. Momentum is not lost. It's absorbed or reflected or whatever, like we talked about. So we can use the equation that momentum is equal to mv, where mass is equal to, m is equal to mass and v is equal to velocity, right? mv. So it's kind of like one part of kinetic energy. Remember, kinetic energy is 1/2 mv squared. Well, momentum is mv, which is kind of interesting. All right. So we go forward. Here it is. So that's the linear momentum of a particle is what we're talking about. And the definition is that a mass m moving with the velocity v is defined to be the product of the mass and the velocity of the particle. And it's a vector quantity because it equals the product of the scalar quantity m and a vector quantity v. Usually when we have a scalar times a vector, we end up with a scalar at the end, all right? We have a direction and magnitude, and we also have, well, we do have a direction, and we have this unit is kilograms meters squared. That's the units, because of course it'd be mass, kilograms, and velocity, meters squared, or meters, sorry, meters per second, not meters squared. It's too early today. So P, momentum, is equal to mv is momentum. Okay, so why is this important for our collision response? Because we have energy. We have energy. And so the faster I'm moving, that's what this means, the more momentum I have. If you think about that, right? It's directly proportional to the speed. So this is why the Flash, if you look at this, and if you we're going to talk about, he's a light guy. If you actually look at the Flash in the comic books, he's not a big guy, but he moves like almost like speed of light, right? When it comes to how fast he is, right? So when he actually hits you, I don't know how his hand would stay, not broken, but if he actually hits you, he's got more momentum. He can actually really do a lot of damage because of the speed that he's traveling. He can travel almost like, let's say, if this is possible in the comic books, if we can actually look at this in terms of realistic motion, because he travels so quickly, he does more damage because of the momentum that he's carrying with him, right? Also, okay, think of a more realistic example. Someone does a spinning back kick. Why is a spinning back kick more powerful than a regular back kick, right? Or some kind of spinning something, some kind of spinning attack. Why do people have spinning attacks, right? Because they build up momentum, right? And when you build up momentum, it does more damage because of this rule, mass times velocity, right? So it's interesting that that's the way it is, but the faster an object moves, the more damage or more energy is going to be transferred from one system to another, right? So if I have a system that's transferring energy, think about a system that's moving, a car, and I smash against another car, I transfer energy from one car to the other. The momentum is not lost, it's transferred, energy transfer, like we talked about before. Okay, and we can break down momentum into different components, X, Y, and Z. Now, again, think about this. We're not going to be tested on this in the final, right? There's the final exam for the people who've come in late, right? People coming in late, look up here. Yes, right? There will be no final exam next week. What I'm going to do is I'm going to give you a take-home exam. One single assignment that you'll do is one question that you'll have to answer by Friday of next week. If you don't answer it by Friday, you won't get a mark for your final exam. It's worth 15%. You'll have to do it on your own, which you would have had to do anyway in your exam period, right? And the reason why I'm doing this is because I'm a little bit concerned with the attendance that I've been getting in class. This is on the programming side. Not everyone has attended, like I talked about before, and I'm concerned. I'm going to make an announcement to this effect as well. But I want to make sure everyone does well, and part of that is giving you a chance to work things through on your own. It's an individual assignment so that you won't be able to collaborate with people officially. However, I'm pretty sure you're going to talk to people anyway, right? Okay, so going back to this, you've got these components of momentum, and you can also say the sum of all forces is equal to ma, and if we replace acceleration with the change delta v over delta t, right? Because you can switch things up a little bit, right? Acceleration is dv over dt, right? If you think about that, the rate of change. Then you can rearrange the equation so it looks like this, where the sum of all forces is equal to the change in momentum over the change in time, right? Okay, so if I want to know the force that is being transferred in newtons from with regards to momentum, right, over time, we can figure this out. And this idea of energy transfer, we have this thing called an impulse, right? An impulse is the change in momentum over time. So it's almost like I have momentum, and as my momentum increases, then I have something called impulse. And actually, if you look at if you're working with Unity, and you have impulse, you can actually have an impulse movement or something like that, where I give myself a little bit of a push. That's what impulse is. A good example of an impulse is I'm playing hockey or some kind of sport, and then I bump somebody, right? When I bump somebody, I transfer temporary momentum to that person. They get some momentum, impulse, right? Impulse movement. And then it stops. There's no more energy being transferred anymore. It's not constant energy being transferred or anything like that. It's just an impulse, something that I'm giving them for one moment. Okay? And actually, that's where the momentary energy comes from. Momentum, impulse. Woo. Okay. So yeah, you can rearrange this thing so you can solve for the change in momentum is equal to the sum of all forces times over time, or times time, right? That's what it works out to be. Just rearranging this equation altogether, right? Impulse it's an integral. And what we do is when we want to try and figure out impulse, we look at, you can see that I'm skipping slides, by the way. It's the kind of the area under the curve when it comes to the time graph. You can see that there's energy here, force, over time. Force times time, right? And you see this energy under the curve for the amount of impulse. And you can see that it's a little bit steep, right? It's not a smooth curve. It's kind of angled, if you will. And that's how impulse would look, because it's a momentary increase of energy and then it's gone, right? Because the time factor is very small, usually with an impulse, right? Okay, I'm not going to go into that one. So because it's like such a short time, we have to approximate impulse, because we're looking at something, or we're analyzing something for a very, very short time. A lot of times we use this impulse approximation, or what we call an impulsive force, and again, I like the word impulse because impulse to me, here's impulse. It means it's got pulse in it. I don't know if that makes any sense to you. I like it's a mnemonic for me, right? When I remember when I was learning physics the first time, I was like, pulse. It's like a pulse. It's like an impulse. It's like a quick motion, and then it's gone. Temporary motion, right? And that's what I think of it when I'm thinking about impulse. Okay. Any questions around impulse and momentum? Yes. And force? It's a different kind of force. It's not different. There's not a difference. There is a force. Impulse is You know, if you go back to what I talked about, it's, you know, momentum over time, right? So if you think about what this is, it's force times time, right? If you solve for the change in momentum, and if you rearrange stuff, then you can see that the change in momentum is actually impulse. That's what it is. The change in momentum, right? And it usually is a very quick change in momentum from zero momentum to lots of momentum, usually, right? Like someone's stationary and then they're being hit by something. Remember, we're talking about collisions, and all of a sudden now they have energy for 1 second, and then it's gone, right? And that energy is enough to push them or push that object or whatever it is in a direction, usually, right? Force over time is like that. That's kinetic energy, isn't it? Right? Force over time, right? So, or work, which is like, you know, but it's not that way. There's pieces missing because it's like a quick, you know, energy and it's gone, right? Okay, let's go back to this. So here's a crash test example. So you have this a car with a mass of 1,500 kilograms collides with a wall, as shown in this figure. The initial and final velocities of the car are v initial, which is a negative 15 meters per second. And if you notice where it says I means on the x-axis, right? Because it's a one-dimensional collision, right? Negative means it's going towards the left, right? If it was positive, it'd be going towards the right. So going easterly to the right is positive. Northerly, north or up, is positive, and so on. Okay, and a velocity final of 2.6 meters per second, respectively. So it starts off at negative, and then it bounces back at 2.6 meters per second. So you have all those things, the initial velocity, which is up here, and the final velocity, which is here. If the collision lasts for 0.15 seconds, that's a long collision. 0.15 seconds is like, you know, 150 milliseconds, let's say, right? And what I'm saying, when I say this is a long collision, you got to figure out that that's like 10 frames, almost, or 9 frames, right? The collision lasting 9 frames in a video game is huge, right? That's like, what's going on for 9 frames? That's like that's almost like I could do a little animation with that collision, right? And find the impulse caused by the collision and the average net force exerted on the car, right? All right, so this is our diagrams, yay. And notice that the arrows point in the particular direction of the wall. There is crumple. That's energy loss, right? Or in our ways, we want to think about this as energy absorption. All right, so there's not a loss. The momentum is being absorbed by the wall, right, and by the part of the car as well. The crumple effect itself is where some of the energy is going, and also it's going into the sound, the big crash sound, any kind of smoke, sparks, heat, all those kind of things is where the energy is going. It's not being lost. Remember, energy can't be created or destroyed. It's being absorbed or redirected, right? So if we go through this problem, we categorize what's happening here, and we want to try and do something like this. We want to say the impulse of the car, again, is the change of momentum, right? Which is momentum final minus momentum initial is equal to, and if you notice what momentum is, it's like saying mass times the final velocity minus mass times the initial velocity, which is just mass times the velocity final minus the velocity initial. And if you sub in those numbers, you can get this number, which is 2.64 times 10 to the 4th kilograms meters squared, right? That's the units that we're using here for momentum, okay? So that's the amount. And then the average net force exerted on the car then, once we have momentum, we know that force, how to figure out force average, which is momentum over time, right? And you take that number we just got and you divide it by the time, which is 0.15 seconds. So it like something like 9 frames, 9 point something, right? Which is 1.7 times 10 to the 5 newtons in the x direction. Okay, does that make sense? So I have energy transfer. Guys, this is important because now one of the questions that I've given you on your assignment, I think is question number 1, is like you're bouncing and you're losing momentum. It says that in the assignment. How are you losing momentum? Where's that going? It's being absorbed, right? Into the wall. So what I'm trying to get you to simulate is, okay, as you're hitting the wall, part of that energy is being lost in the collision. That's what I'm saying, I'm leaving it to you how much part it is. I'm not going to specify because then it'll be very scientific, and it's not a simulation, it's a game, right? So I want you to figure out for yourself a realistic number, amount of energy, or in your case, velocity, that's being lost, right, as you hit the walls, right, as you bounce. Okay, so that's what this is all about. This kind of tells you how it works, and this is one of the probably the most important thing because we're doing these kinds of crash or collisions, you know, in video games. Okay, so again, collision, it represents this event during which two particles come close to each other and interact by means of forces, the physical definition. And we can think of this example of two particles that are colliding and then they go the other way. So I have this. So in this case, I have mass number 1 and mass number 2. Mass 2 is going this way, right? Mass 1 is going this way. And when they collide, they change direction in this particular. It's a one-dimensional collision, right? Now this is kind of a weird thing. How much does does this one, the smaller particle, go this way compared to the larger particle going the other way? It's probably going to be more. In fact, if it's a much larger mass, it's probably going to be at least twice as much. All right, depending on how large it is. But in the same thing, what it says here is momentum is conserved because at the end of the day, energy is not created or destroyed. It's a closed system, right? We have two types of collisions. There's an elastic collision and an inelastic collision, right? So there's different kinds of elastic collisions as well. There's a perfectly elastic collision, almost like a perfectly bouncing ball, right? That's elastic collision. And they usually don't occur in the real world. You don't see a perfectly elastic collision. Why is that? Because of energy absorption. Okay, so a perfectly elastic collision's happening, at the microscopic level between atoms. There we go, right? But at the macroscopic level, in the real world, we have energy loss because of deformation, sound, like we talked about, crumpling, all that stuff, right? And it's not really lost; it's being reabsorbed and I don't know, targeted to different, kind of stream in other places, right? So we don't say lost is a weird word. It's not really lost; it's just absorption. All right, so perfectly elastic doesn't really happen. It's elastic or inelastic. Okay, so inelastic collisions, energy is not conserved, and although the momentum is still conserved, the energy is transferred, right? A good example of that is if two objects that collide stick together, right? What happened to the kinetic energy, right? It's one is added to the other one, as an example, and some of that energy, the kinetic energy, is lost or transferred, usually down into the ground, believe it or not, right? Or through sound or whatever, right? Okay, so that's the inelastic part. Inelastic is when two things stick together. If two things are sticking together, it's an inelastic collision. Okay, elastic collision is when things split apart and go the other way. All right. Okay, let's keep going here. So again, in perfectly inelastic collisions, right, where we have these two objects, they're colliding and then they both go in the same direction afterwards, right? Typically what you have is you have a set of equations that I'm not going to go over because you don't need them right now. I'm mentioning it again. The PowerPoint that I'm putting up here is for completeness. So you have a whole picture of what you need to use. For next time you hit physics 2, that you're going to do actually stuff with Unity or whatever, you're going to use some of this more, but I want you to use these as kind of a reference slides, if you will. It gives you enough information for that kind of stuff, right? But basically what this is saying is the final velocity that you're going to get is you take the, the momentum, the initial momentum of object 1 and the initial momentum of object number 2, two objects, and then you divide them by their respective masses to get the final velocity, right? So this is the perfectly inelastic collision, right? So momentum is preserved, but not kinetic energy, okay? Elastic collisions are like a ball bounce. So here you have these two objects come together and they bounce apart, right? That's elastic collisions, all right? And that's really where I want you to kind of take that, right? So if the two objects bounce apart, usually there's an elasticity. I also like to think about it as if you have a bouncing mechanic, it's also called restitution in physics. Restitution is more or less the amount of bounciness, right? I don't know if that makes any sense, right? Bounciness. Hey, that's a real technical term. But that's what we're talking about when it comes to elastic collisions. Okay, and again, there's a set of equations that when you have these two equations, you have kinetic energy as well as initial momentum, and then what you want to do is figure out mass or something like that and use systems of linear equations to figure that out. However, it all comes down to velocity, which a lot of times with some algebraic manipulation, you can get rid of mass altogether because mass becomes irrelevant. You have the initial velocity of object number 1 minus the initial velocity of object number 2 is equal to the final velocity of object 1 plus the final velocity of object 2, which makes sense because momentum is preserved. So when you add those two velocities together, at the end of the day, you still have the same amount of energy there, right? In terms of that one part of the energy, the velocity, because momentum is made up of both mass and velocity. And again, there's some more equations you can use to figure out if you wanted to find velocity 1 or velocity 2 for the final, you could take the initial numbers and use these set of equations to figure this out. You may need to use this kind of stuff when it comes to two objects colliding, all right? Now, this is supposing that the two objects have different masses, but they're not wildly different. Okay, like not double the mass or something crazy like that. They're somewhat similar, but not exactly, and they're not at rest. Okay, there's a situation where both these objects are moving. Okay, but there are some special cases. So one case is where mass 1 is equal to mass 2. An example of this would be you're playing a pool game. You have two pool balls or cue balls, right? And one pool ball gets hit by the other one. One pool ball is at rest. You have the white ball, and you hit the white ball to hit a colored ball. When you do that, it transfers energy from the white ball to the colored ball. And what ends up happening is the white ball typically is at rest if you hit it properly, and the colored ball it gains momentum. It transfers the momentum from one ball to the other. Why? They're roughly the same mass. That's a special case. Normally, you don't get things exactly the same mass hitting each other, typically, right? So this is a special case, and so therefore, we have a second set of equations for this kind of case, where we have two balls the same size or two masses the same size hitting each other, and one is at rest, okay? The other case is if you have a really heavy-duty mass, like a massive bowling ball hitting a cue ball, right? That kind of thing. And one of the object is at rest. So, for example, when the very light one is at rest and it's getting hit by the, let's say a bowling ball hits a cue ball, then the bowling ball is going to basically, or the cue ball is going to take on about twice the speed of the bowling ball, which is kind of a weird thing because it's so massive. It's just a property of how this thing works, right? And if it was the other way around, if the bowling ball was being hit by a cue ball, it's massive, big mass compared to a small mass, on a head-on collision, and if the heavy particle, the heavy bowling ball, is at rest, right, then the cue ball would reverse direction and go back the other way, right? So velocity is reversed, and the bowling ball pretty much would move, okay, because it's so massive. So again, this is just case 1, case 2 of these elastic collisions, okay? Again, this is the physics lecture part. Please forgive me. I know this is not the most exciting part, but it's an understanding of how motion is transferred or energy is being transferred from one component to another, all right, or one part to another in a system. And it talks about how to solve. This is another example of you have this stress reliever, the executive stress reliever. Yeah, so that's what this problem is called, where you swing a ball, it's tethered, and then it hits another set of balls, and what happens is only one of them pops away. Why is that? Because it's being transferred from one ball to the other until the energy is finally passed to the last one, right? And so you don't have a lot of movement in the middle, right? It's just the last two that seem to be popping away, right? And if you look at this, it kind of looks like this. This can happen where you do this, but this doesn't happen because you can't move twice the mass with the same momentum. That's the idea, okay? And that's why this all works the way it does. Okay, and it also talks about this ballistic pendulum. I'm not going to go into too much, but basically the ballistic pendulum is like firing a bullet. And what it does is it strikes a mass, and it kind of comes up. And again, it's kind of the same thing as a pendulum moving back and forth, and how that all works when it comes to an object that's being tethered. right? A pendulum and a ballistic pendulum of that is something that you're firing a very high a velocity, an object with a lot of velocity and momentum hitting another object that's at rest, that's tethered, okay? Which is, again, is kind of weird, right? Okay, and I have some set of equations for that. Two-dimensional collisions, and this is where we get more interesting. Again, we have, in this particular case, the reason why it's two dimensions, notice that it's a glancing blow, okay? So we're not actually hitting this thing dead on. We're hitting it on the side, right? So the part of this thing is going to be hit. Again, example, the cue ball. White ball hitting the colored ball as an example. Once it hits the colored ball, you have this example where the two balls go in different directions, all right? And there's a set of equations to calculate how this works, how this glancing collision would work, right? Where you have some of the energy going here and some of the energy going down here. And again, if you notice, V sine theta is on the y-axis and V cos theta is on the x-axis, which is very similar to what we saw with kinematic equations in the past, okay? So that just to show you how this looks, right? And you're going to see some of this when we actually saw almost this exact thing with two pucks or a puck being hit by two different sticks, that kind of example from a last module that we had, okay? So this same example is where you have two objects that are glancing off each other. Now, this is really great if you're making a game that has a bunch of particles or something that like is literally glancing off each other. But it's a rare case we see this, right? Okay, and talks about how to figure that out. I'm not going to go into that. This is a very common thing. You have two objects. You have a car, which weighs 1,500 kilograms, and you have a truck going this way, which weighs 2,500 kilograms. One is traveling at 25 meters per second this way. The other one is traveling at 20 meters per second. Notice this says I and J. Think about I's and J's for those people who forgot as X and Y, right? I is on the exerly direction, X and Y, and J is on the Y axis. And then you have resulting energy that goes this way, right? Two objects hit each other and they're both going in the positive direction. That means it's going to go towards the top right quadrant, which is, again, both positive X and positive Y, right? And if you look at the equations for this, you can see that is exactly what's happening, right? You have two equations, right? You have total momentum or change of momentum on the x-axis and change of momentum on the y-axis. And you have two little equations here, right, which is broken down here. And then what you do is if you want to find the, you take equation 1 and divide it by equation 2 divided by equation 1, right? And then what you end up getting is this idea of tan theta, right? Where theta is the inverse tan of m2 v2I, which is the initial velocity times the of the second object times the second object's mass over the initial object's mass. You sub in the numbers and you get this number, which is 53.1 degrees. That's the angle that things are splitting off towards the right. It's got to be towards the right, a positive angle, because it's in the top right quadrant, right? So if you're going to figure out where it's going to go, two objects colliding, this is the way to figure it out. And if I wanted to find the final velocity as an example, then I can figure out that the final velocity of those two objects merging, what kind of collision is this? Two collisions, elastic collision, inelastic. Which one is this? Inelastic, because the objects are moving in the same direction. They're combining, they're almost joining and becoming one big crash, right? And they're moving towards the right. That's an inelastic collision, right? And they have a combined velocity at 15.6 meters per second at the end, okay? Again, going back up to the picture, right? Two objects merge and become one as they move towards the right, okay? Okay, the idea of center of mass is important as well, because a lot of times what we have is we have an object and maybe it's irregularly shaped or whatever, and whether we're modeling it or we're programming it, right? We look at the center of mass as the object as a particle, right? This idea of center of mass. And sometimes the way we can figure out center of mass is where we take the sum of all masses across the x-axis and the sum of all masses across the y-axis and the sum of all masses across the z-axis in 3 dimensions, and you find out the center of mass if you really want to know where that is, all right? But for us, at the end of the day, what we want to find out, and I'm not going to go into too much of this, is where we have two masses. This is an extended object like an arm or something like that. which is part of the whole, right? And it talks about how to figure out the, kind of one part of the mass, which we're not going to do. This is just, again, just for completeness. I put it in here if you need it, right? But center of gravity is very similar, where we can look at kind of the places where the object is being kind of held, or if you think about it, I've got these two things that I'm holding. I'm suspending this wrench as an example on a particular spot, right? And where is the center of gravity? It really depends on where it's being held by and compared to the center of mass. Okay, so I'm not going to do that. And this talks about systems of particles moving together, where you can use Newton's laws for moving whole particle systems together. So I have this massive group of particles. Where's the center of mass? You can figure it out where the most dense area is. Actually, if you take a cross section of all the particles, you can figure out what the center of mass is and treat it like one big object, right? But again, small use case for this kind of stuff typically. Okay, at least from a game perspective. The other thing is when you have an explosion, this kind of idea, you have an object that comes up, a projectile, and halfway through the motion, it explodes, right? So what happens is in physics, the parts of the projectile continue to rain down in the same spot where they're supposed to go in the first place, approximately. Okay? So notice that if I had some kind of missile, this is interesting, right? And if I had a missile that would split off somehow, so let's say I had a missile that had multiple warheads, right? And I was aiming for a specific spot and I wanted to do the maximum amount of damage, I would split the missile at a certain point, right, where in its downward trajectory, and I could hit a much larger area and do way more damage, right? Or even if I exploded something close to the ground, close enough, the debris that would rain down would do a lot of damage still. Okay, so just kind of an idea of how this would work. Again, rocket propulsion. If you want to be a rocket scientist, read this part, right? It talks about how to transfer energy between rocket fuel and moving. I put it in here again for completeness, and it talks about how I have a bunch of energy. I've got fuel inside the rocket. Fuel has mass, and mass is being lost because it's being consumed. Mass is being consumed as the rocket moves, and that's why it's rocket science, because mass is changing. It's not a constant mass, right? And it's really difficult to calculate where the rocket's going to be based on the mass, and the speed is going to also change, okay? So it's right here, and also this idea of thrust, okay? So those are the things that, what stuff we wanted to talk about. All right, and this kind of slide is a little bit out of order, but the idea is that collision detection and collision response, or collision resolution, they're two different things altogether. And we've just talked about the physics side of collision response, which is momentum and impulse. I want you to think about that, momentum and impulse. Energy being transferred, again, and momentum is not lost, it's conserved. However, sometimes kinetic energy is absorbed, right? Or what we see as lost. Okay, any questions so far on the physics side of things? So physics is done. That's the last physics you're going to hear from me for this semester. Yay, right? Here's the programming part that I'm going to give you, right? So part 2. So there's some cases, right? You got a bouncing off horizontal and vertical walls. Again, see question 1 on your assignment number 3. This is what's happening here. Bouncing off inclined walls. That's a totally different situation where you have some kind of incline, maybe like a slope of some kind, and you're bouncing off that. That's a totally different situation than the first one. Collision between two particles in 1D, two particles on the x-axis colliding, right? Collision between particles in 2D, two particles colliding, and they glance off each other, like we talked about, a glancing blow, right? Those are different kinds of situations that you can encounter, and they're very common. Okay. How about bouncing off horizontal and vertical walls, which is what you need for assignment number 3. So the idea is here that you have this idea of elastic and inelastic bouncing, right? What's inelastic bounce? There would be no bounce. It would just stick, right? Because remember, two things stick together. When they're inelastic, there's like maybe the ball would crumple or it would just explode. I don't know. But you know, an elastic bounce is typically what we think about when you think about a ball. Again, we have this kinetic energy, which is 1/2 mv squared, right? And then we get this situation where we have, if it's bouncing directly with no angle on a horizontal surface, v becomes negative v. It's pretty simple, right? I mean, that's the first thing. If you're actually hitting the surface at the normal, right, perpendicular to the surface, you're going to get just a reversal of velocity, okay? And some energy loss. Some energy loss, all right? Why? Because in a perfect elastic situation, perfectly elastic collision, no energy loss. But that's not realistic, right? And in your assignment assignment 3, part 1, it says you lose momentum. Even if you did this, you would lose momentum. Why? Because some of the energy would be, you would hear the ball hitting the wall. Perfectly elastic means there's no sound either, somehow, right? And there's no friction whatsoever. It's a completely frictionless surface, no sound. It's in a vacuum somehow, and you're hitting a wall with a ball. Even then, you're going to get some energy loss, right? So that's not realistic. That's why it's in the microscopic level it happens. But macroscopically, it's almost impossible to have a purely elastic collision. In a game, though, there you go. There's the microscopic level. In the game, you might make it perfectly elastic because that might suit your game from a game mechanics perspective, right? But realistically, it's not. It can't be done. It's not possible. One of the challenges we have when it comes to bouncing is this idea that between frames, right? So going back to the programming part, between frames, you're going to have a situation like this, right? Where you have a ball and it's not going to stop here. It's going to go through, right? What you need to do is when you actually draw the ball is bring it back out, right? So you start, you know, when the ball goes through, you literally bring it back and then change its direction, okay? You start at the wall because it wouldn't have gone into the wall. The reason why it's going into the wall is because of the heartbeat of your game loop, right, is only every so many frames. And depending on how fast your ball is going, you have this tunneling effect of projectiles, right, where it's going to go through the actual object, right? And again, we talked about last week swept spheres, different ways of detecting collision between a particle and a plane and this kind of thing. But when it penetrates the wall, you've got to bring it back out and then reverse the direction. Okay, so that's one of the challenges we have when it comes to resetting or repositioning the object that's hitting the other object. Okay, if you want to have more realistic bouncing. And we haven't talked about the 12 principles of animation. Anyone know what the 12 principles of animation are? Some people? One person? Got a person in the back, Nicholas, you know? Yay! Okay, 12 principles of animation. There's a principle that talks about stretch and squash, right? So a lot of times what happens is when a ball hits a wall, the ball hit the wall. It was one of my first nursery rhymes when I was like, I think it was when I was, I don't know, 1. Anyways, what ends up happening was you get this squishing happening where the ball is actually squashed a little bit and the volume expands slightly, right? So this is stretch and squash kind of idea, right? And then what happens is it kind of reforms back and then pushes back out, right? And then it elongates slightly, right? And you don't see it right away. And it's hard for us to see it because our human persistence of vision can't detect those kinds of things unless it's a big wobbly water balloon. If you ever throw a wobbly water balloon against the wall and actually bounces, you see it kind of stretching and elongating and deforming, right? It's happening for the ball too. We just can't see it fast enough, right? But if you want to make a ball in a game look good, you can do that. You can actually create this stretch and squash animation where it hits, you squash it and you stretch it a little bit longer, keeping the same volume. And then when it rebounds, you change the volume in again, and then you elongate it, and then it goes back to its normal shape, right? So this idea, and I'll show you a quick video about the 12 principles of animation today, just to give you an idea of what that means, just that one part. But I can't do it here because I'm recording, okay? Yeah, so elastic bouncing. And then we have to do this repositioning stuff we talked about before, and there is an example of this where we have ball X, the X coordinate of the ball, and the X coordinate of the wall in this particular case, minus if this is greater than the ball radius somehow, right? Then what ends up happening is we want to have the ball X coordinate equal to the wall coordinate minus the ball radius. So that way it's repositioned. And then we change the velocity of the ball so it's the negative velocity. This is a very simple equation. This is, again, the only time this happens is when we have a perpendicular attack on the wall, like exactly perpendicular or to the normal of the wall, which is rare, right? Unless you have a Pong game where it's like literally going from the right side of the screen to the left side of the screen, or vice versa, right? Or up and down. What about in this case, where we have some kind of elastic bounce, but it's happening at an oblique angle, right? And this is more common. Yes? Okay, there you go. All right, I mean, that's how it is. So if it's going like this, again, what's happening is you're going to get the same amount of vertical force. You're not going to reduce that, right? So the easiest way to do it is reposition the ball out. That's the first thing you would do, right? Because you need to do that, right? You can't just, you know, reverse direction from here. It would look weird, right? Reposition, and then what's happening is on the x-axis, I'm going towards the right, right? And now you're going to reverse only the component on the x-axis to go to the left, like you said, right? But the component on the y-axis stays the same, well, or slightly reduced in case of our assignment question. So you want to reduce the energy on one of the components of the motion, right? Yes. Every time it hits the wall. Sorry.
Are we also supposed to reduce it like over time?
No. But if you want to make that, if you want to make a smooth step kind of reduction, it's up to you. Like a lerp.
I just did the opposite. I made elastic velocity.
Okay, that's not really what I wanted, but it might be the same. Might look the same. It looks the same. It might look the same anyway. So it's fine, right? As long as you look slightly different, and then over time it would just slow down and stop, then I'm good, right? Yeah. So again, this is a situation. Now, here's the thing. The angle of incidence here, right? I have an angle of incidence. I always look at that, right? So I've got the angle here, this angle here that goes from the surface to the ball, right? When it comes out, guess what? That's going to be the same angle, right? There's going to be a bit of friction, but it's more or less it's going to be the same, roughly the same angle, right? So that means that, well, the same reverse angle, right? So again, if this was something like, let's say 15 degrees, then this would be something like a negative 15 or whatever would be the other side, right? So, but it'd be the exact same angle, just reversed, right? And what does that mean? It means that if I come closer and closer to the perpendicular, right, I'm going to be closer and closer to coming right back at me, like almost like a zero angle. If I'm farther away, it's going to bounce, you know, kind of at the same angle away. Hey, guys, this is back to pool again, right? If you look at a pool ball and the sharper the angle I am, then the sharper it's going to be on the other side, right? So the steeper angle I am, it's going to come right back at me. So if I want a ball to come right back the other way, I'm going to hit it against the corner or the side of the pool table, and it's going to come right back at me. So this is kind of simple physics, bouncing, right? Actually, pool itself is the most elastic bouncing you can think about getting because the sides of the pool table are more elastic than normal, right? They more restitution, a higher level of restitution. Lose some energy whenever you hit the wall. A little bit more inelastic than elastic, okay? And we talked about this, but you can also multiply it by some kind of factor of loss. This is what you could use in your assignment number 3, all right? So it's a negative V times some kind of factor. Whatever that factor is that, you know, maybe you lose 5% of your energy when you hit. I mean, in games, you can do something like that. It doesn't have to be perfect. I'm not asking you to calculate the mass of the object being hit. I never said that. Right? How about being hit with the paddle? So how do I figure out how much energy is being transferred, you know, from the paddle to the ball? It's momentum, right? Mass times velocity. In our case, we don't even care about mass. Velocity. The higher velocity is for the paddle, the more energy being transferred to the ball, and then that energy should be maintained. That velocity is going to be transferred, some portion of it, so it increases the speed, and then as it hits the wall, it decreases the speed. So you could have another factor, a factor that increases 1.1. 10% faster when you hit, or relative to the speed of the hitting, and then reduction when it comes to hitting the wall, okay? So some strategies in terms of how do we do assignment number 3. Okay, Bouncing off incline walls are more challenging because now our horizontal and vertical components are not straight, right? As an example, an incline walls would be things like ramps and those kind of things, okay? So we have to do that whole coordinate rotation thing that we talked about when it had an incline. Remember that whole car on the incline question before? We have to rotate everything. So it's going to be like this, where we have the normal is not on a vertical or horizontal, but at a different plane altogether, right? And then what ends up happening is once we do that, the vectors change. So it's not v cos theta anymore for x, and the x-axis and the y-axis is v cos theta, and the x-axis is v sine theta, and so on. You reverse them, and then you have a different way of doing the energy, right? So the energy kind of comes off. But the problem with this is, again, you have these two angles. You have an angle of incidence and an angle, kind of angle of attack, and then the response angle. And it would be like you're calculating what it's going to be based on the surface normal. Whatever the surface normal is, you're going to have an angle relative to the surface normal, and that's the response angle that you're going to get. Okay. Trying to think of something that can help you decide this. We don't have this case in our assignment. I'm just putting it here again for completeness. But basically, you have these equations where ball to wall 1 is you have the wall on the point on the surface, and you subtract the ball position 2 in 2D, and then you get that ball to wall 1. And then what you do is you want to get the projection of the ball on that particular plane, and then from there you get the so this basically the surface normal is what you're using to get the new angle. Okay, again, on this case, you still need to position the particle again. So this idea of repositioning the particle, you want to position it here. The momentum is going to go through the wall, but instead of the momentum going through the wall, what you're going to do is you're going to re-angle the momentum to the location where it's coming out of. And by the way, this wall could also be the edge of an object. So I have a big two-dimensional or three-dimensional object that's moving around. More challenge because now it's moving, right? And you have its own momentum, its own energy, right? And it hits at a particular angle. You need to respond to it somehow, right? What about this brick that you have in assignment number 3? You have this brick walking around. I know some people thought about the brick as like a brick like this, like flat, vertical. I keep thinking about it almost like a paddle that moves like this. You might put it at an angle. Don't do that, right? It just makes it more difficult for you. I mean, or allow your player to choose the angle of the brick. I don't know why you would do that craziness, but if you really wanted to, that would be more challenging, right? Because then, depending on the angle of the brick, that would justify not only the speed but also the angle of attack up against the wall, which would make for the game to be more difficult, almost like an angled brick breaker, right? Which is kind of weird. Okay, so when repositioning is important. You have to reposition it back out, and then. Okay, now you got to figure out how much energy. So I've got this energy happening, right? And then I hit the wall. How much energy is left? How much energy is absorbed? And how much energy is going to be reflected, right? Because this momentum is going to be conserved, right? So I've got this, remember, it's mass times velocity, right? So whatever the mass is, let's suppose it's moot, mass of 1, right? 1 kilogram, 1 unit, right? Then I have velocity. Velocity is what we really care about. I got this velocity, energy, and I want to turn it the other way. Right? But how much do I turn the other way? Especially if I have a limited amount of energy. Impulse. So I've pushed something towards the wall. It doesn't have its own energy. It's not traveling with its own power. Right? I've pushed something against the wall. How much energy is being lost when it hits the wall? Especially if you have a friction-based surface, right? Where energy is constantly being lost. Right? And this kind of idea is what you have to do is reposition it. And then once you've repositioned it, the angle of attack is going to be the angle of response, whether it's against an incline or against a straight wall, horizontal or vertical. And we have this little equation, which is the displacement, which is the radius plus the distance dotted with the normal, dot product, normal. The normal is the perpendicular a vector perpendicular to the surface, right? And then over sine theta, where theta is the angle of attack. Okay? So you can use this equation easily to kind of calculate the new destination, the displacement, based on what the angles mean. You can also solve for the angle. What's the new angle? as an example, based on the total displacement, that kind of stuff. And I'm not going to go through some of this, but at the end of the day, this is how it works when it talks to calculating the new velocity, because the velocity would change based on the angle of attack, right? Okay. And I've given you some code here, some pseudocode to help you out. If it's going to be a ball bouncing off an inclined wall, which chances are in your assignment number 3 you won't need, right? But just in case, here it is. Okay. Collision between particles in 1D. You have two particles, they collide, or two objects that collide. And what you want to do is you want to so a few steps: collision detection, right? We know how to do different collision detection now. We've talked about it, different ways. Most two common ways are AABB and some kind of circle-circle or sphere-sphere collision, right? That's the most common methods. And then we have this idea of repositioning the particles at the moment of collision. Normally, what we do is in a 2D game or a 3D game, they explode. But in this case, we want to keep them, and we want to reposition them so they look good, and then calculate the new velocities and the directions based on the collision. All right, and that's the methods we're going to use. I've given you some examples here of how to use it with spherical particles, and the idea that these two particles collide again. You want to separate them and then go in the opposite directions, depending on the mass of the particles. Similar stuff to what we've talked about before, okay? And 2D, again, we've talked about this, just two different components. I'm not going to go into too much detail. Again, just as an overview, detecting the collision, decomposing the initial velocities in normal and tangential components, tangential being tangent to the sphere or the circle in this case. So how much of a glancing blow is it? How much of the X and Y energy is going to go away, right? And then reposition them so that they're in the right place at the moment of collision, momentum of collision, right? And then calculate the new normal velocities just after the collision. We saw that in the physics side. How do you calculate those things, right? And I've got your equations for you if you want to use it. Okay, and then we have a little bit of pseudocode to help you out in terms of how this would work, okay? It's just a little bit, right? By the way, you can make this a lot simpler because remember, you're controlling the game, you're controlling the velocity, you're controlling everything, right? So you can simplify this and make it less realistic, but more playable. Yeah. And that's really most of what I want to cover today. Again, I'm just going to stop recording now. We've gone for about an hour, but I want to show you a little bit of the 12 principles of animation when it comes to stretch and squash. And then I'm going to talk about, again, your exam next week, okay? All right.